We're going to look at how to calculate equilibrium constants using statistical mechanics. Right. This is kind of like a lot of things involving statistical mechanics. It's a little bit of an unusual notion to think that we can start with what are essentially spectroscopic data about the energy states available to molecules and use those to calculate an equilibrium constant for an actual reaction. Right. In this video, we're going to look at just sort of the conceptual framework of how to do that. And then in the next video, we'll look at a rather grisly calculation in which we, among other things, demonstrate that while it's possible, it's not that much fun to do. So we've derived a relationship for G, the Gibbs free energy, right, based on the partition function. And that's the top equation that's up here, right? So this says we can find a value for the Gibbs energy for a particular substance, all right? It should make sense that if we can calculate G for the various things involved in a reaction, then we should be able to calculate delta G for the reaction. If you think back into Gen Chem or what have you, if we know delta G, we can also get to the equilibrium constant for that, right? Because delta G and the equilibrium constant are really two different ways of expressing what should be the ultimate outcome of a reaction. Where does it thermodynamically want to get in terms of the composition, the mix of reactants and products, okay? So that says if we can get delta G, we can get the equilibrium constants. That means it should be possible to get from our partition functions, where we've got our Q in there, right, which is the whole molecular partition function for whatever substance we're looking at, right? So we're going to look at how this works and what it can tell us and how to make sense of it. Before we do that, there's one thing we need to fix, and that is we need to stop playing loosely with where the 0 point is for energy. Okay, whenever we've calculated our partition functions, we've because it makes life simpler, we've always set the lowest energy state, the ground state energy. We've just called that energy 0. All right, and that's been fine because we've only been talking about one substance. We haven't been trying to react anything or convert one thing into another. And so in that case, just like in a potential energy problem, we really get to pick anything we want and call it the 0 of energy. If we have things reacting where we've got one set of molecules on the reactant side, another set on the product side, now we have to be more careful, okay? Because we have to make sure that while it's okay to pick where we want the 0 of energy, we can't pick it more than once in one problem. Right? And so I can't calculate the partition function for the reactants based on 0 energy equaling the ground state of the reactants, and then calculate it for the products with the 0 of energy being at the ground state of the products, because that would mean I have two different 0 points, and that'll break the calculation, right? It should make sense that that wouldn't work to us, okay? So we have to make one choice in order to get this right. The one choice that is the most common to make and probably the easiest to make is to say that we're going to put the 0 point of energy, just our arbitrary E equals 0, at a situation where everything, our reactants and or products, are completely dismembered into atoms, okay? So we've broken all of the chemical bonds. We don't have anything bound to anything. We just have a collection of free atoms, right? And that's the state we're going to label as being the 0 of energy. To make this a little bit more concrete, we should look at something simple. And so we'll start with thinking about what is basically, you can call this the simplest possible chemical reaction. Take a diatomic molecule like hydrogen and imagine breaking it in half, right? Here's an energy curve, which we've seen before. This is the hydrogen potential energy curve, right? Energy on the y-axis, distance between the two hydrogen atoms on the x-axis. So down here in the bottom of this well, we have our H2, right? So this energy right there, that represents the ground state energy for the H2 molecule, all right? Up here, this says this is H plus H. So that's now what we're going to call the 0 of energy. So we're going to move the energy scale so that 0 goes up here, okay? If I do that, where is the 0 of energy, or what we've been calling the 0 of energy for the hydrogen molecule? It is lower than this 0, right? So it's going to be negative, and it's going to be negative by an amount equal to this quantity labeled as D sub 0. That's the dissociation energy. Right? Easiest way to think about that is if we had a hydrogen molecule in the V equals 0, J equals 0 state, so it's in the ground rotational and vibrational states, then that D0 is how much energy we would have to supply to be able to break that hydrogen molecule in half and get from H2 to 2 H's. Okay, and so that says if we're going to call the 0 up here, we're going to have to shift the energy by an amount equal to that dissociation energy, right? So instead of putting 0 down here, which is how we've always done our calculations for partition functions, now we're going to move it up to there, okay? And again, the reason for that is if I had something that had a more complicated reaction going on, I'd have to make sure that I was using the same 0 point for the different molecules, the reactant molecules and the product molecules, okay? So that's the notion behind how we're going to do this. Your textbook refers to a quantity that it calls delta U, 0m. The m is for molar, and so this is the difference in the 0 point energies for the reactants and the products, okay? And so I've got a little diagram over here which is going to attempt to show us what's going on. So this line up here, this is now where I want to put E equals 0, right? So this is free atoms. That top black line represents taking the reactants apart into atoms, and obviously the same collection of atoms could be used to make the products, okay? So if I look at where this is let's call this U0M for the reactants. Down here, and you'll notice that is lower than where we put 0, and it's lower by an amount equal to the dissociation energy of the reactants, D0. So that says U0M for my reactants certainly is equal to minus D0. The same thing should be true for the product. So over here, this is my U0M quantity now for the products. It's also lower than where I put the 0, and it's lower by an amount equal to the D0 for the products. And so that says for both reactants and products, whatever substances are there, I can say that this 0 point energy, U0M, is equal to minus D0. Okay, I want a quantity that is the difference in those U0M values, delta U0M. So to calculate that, like anything else, the delta means take the value for the products minus the value for the reactants. And so if we do a little bit of algebra down here in the equations, you can see that gets us to a result that says that our delta U0M quantity is equal to the D0 values as reactants minus products, okay? The flip there to get it to be reactants minus products is directly because of this minus sign up here that says that U0M is minus D0, right? So it's minus D0 for the products, minus D0 for the reactants, and that gets us to the bottom line there, okay? So if you're doing a calculation and it calls for this delta U value, the difference in the 0 point energies between the reactants and the products, that tells us we get that from the D0 values, which we can look up. There's actually a table in the textbook that contains values of that for a number of common small molecules, which you might need in doing a homework problem or two. So how are we going to get to an equilibrium constant? How can we think about how the equilibrium constant is related to the ideas we've been using from quantum mechanics and talking about in statistical mechanics? All right. What does the equilibrium constant tell us? It basically tells us how much reactant and how much product should be there when our system gets to equilibrium. Okay, what is the relative mix of those two things? Do we have almost all products, almost all reactants, some more even mix, what have you, right? So the way to think about this is to say we want to form a Boltzmann distribution across all the states that are available, whether they're reactant states or product states. Right. So what statistical mechanics does, remember, is it says take the ladder of energy states and it just figures out based on the spacing between those and what the temperature is, what is the probable distribution of things among those states, right? Now, if I have my reactants and my products, essentially there's just more energy states available, right? Because I can have things as reactants and those will occupy the energy states that are available to those molecules, or it can be converted to products then they can occupy more energy states in the product side. And so there's just going to be a bigger spread of energy states that we can fill, and how that population will be distributed is going to depend a lot on things like whether the reaction is endothermic or exothermic, and on what the spacing and the number of energy levels are that are associated with the different things. What I've got in here are a couple of pictures like this that just have some cartoons in them, basically, that tell us something about how this would work, okay? So this is meant to be a very general equilibrium. The simple equation up there that says reactants on the left and products on the right with our equilibrium arrow just says we're not specifying in any real way what those things might be, right? In the energy diagram here, like always, energy is increasing as we go up. The R here says that on the left-hand side, we have the states associated with the reactants, okay? And on the right-hand side, we have states associated with the products. This particular reaction looks like it's endothermic, because if I go here, this is the lowest energy available to the products. Down here, this is the lowest energy available to the reactants, right? So my reaction overall is uphill in energy. So it's an endothermic reaction. If that energy, all those energy states are available, so imagine that I look in the middle of this diagram and I say, well, here's my distribution of my available energy states. What's going to happen? The most populated state is going to be the one on the bottom. So that says, in this case, I'm going to have, at the temperature that this figure represents at least, I've got a lot of reactants and not a whole lot of products, right? If I look at the length of these maroon bars here, those are meant to depict populations, right? So the long bar down here, this says this is the most populated state, right? As I climb up in energy, my bars get shorter, meaning that my populations are going down. They have to do that, right? We've been looking at these things for long enough. So when I get up to this one, say, which is the lowest state of the products, you'll notice that the bar associated with that, which is drawn over here on the right-hand side, but we can imagine just smushing them together, right? The length of this bar is in between this one and that one, right? So that's what should be, because it's at an energy between those two, right? And then as I go up, I get still a decay of populations. Here, I get this population. The highest one that we've drawn there is a little bit shorter than the one over here, because that state is at a slightly lower energy, right? So that shows me how this would work. And the notion is, again, that what I want is I want to get to a Boltzmann distribution of populations spread across all the energy states of both sides of the equation. Okay. In this case, the fact that the equilibrium constant seems to favor the reactants is very much related to the idea that this is looks like it's a fairly significantly endothermic reaction, right? At least on the scale of the amount of energy that's available here, that delta E value, the difference between the ground state for the reactants and the products, is looking pretty large. We know in equilibrium that enthalpy matters and entropy also matters, right? If you think about how you get delta G, it involves delta H and delta S, and delta G is related to the equilibrium constant, right? So the entropy part shows up in what, if we're being fancy, we could call the density of states. If we want to think about this more in terms of the diagram, it's talking about the spacing between levels, right? Are the energy levels close together or are they far apart? Okay. In this case, I still have a reaction that's endothermic by at least a little bit, right? Which means the most populated state is still the ground state on the reactant side, right? But the energy states of the reactants are pretty far apart. We would say that means it has a low density of states, right? It's a pretty steep climb to the first excited state for the reactants. The products on the other side, the ground state's a little higher than the ground state of the reactants, but the spacing, the separation between my energy levels is much smaller, right? So here I'm going to get a more substantial population of products just because as we go up, the most populated state is still the one on the bottom where the longest bar is, right? But then I've got substantial populations in a number of states here before I get to the next available reactant state over there. Okay, and so that kind of is how the idea of this density of states, or the entropy part, mattering to the equilibrium constant would show up in there. Okay, and so those are meant to tell us just a little bit about how we could think about these things and how we can make sense of the idea that we can do a calculation to get to the equilibrium constant from the sort of data that we've got. I stuck in what, again, in a normal class, these would be like clicker questions or something like that, but I like to leave them in and still let you think about them for a moment. This is a question you probably should be able to answer if you remember your Gen Chem, but we can also talk about it some in the context of what we're looking at now, right? So it says, for an endothermic reaction, what happens to K, the equilibrium constant, as T increases? Okay, as the temperature increases, reaction is endothermic. So you can take a second, you can pause if you want, if you need a moment to think about that. I feel silly if I just sit here and don't do anything. So I'm going to go ahead and say, if my reaction is endothermic, that means, gosh, the way we teach this in Gen Chem is to say Le Chatelier's principle says that heat is like a reactant, right? And so if it's endothermic, that means when we raise the temperature, the equilibrium constant should get larger, and I should get more product by raising the temperature if the reaction is endothermic, okay? We can think about that in terms of these diagrams. This reaction is a little bit endothermic, right? It's climbing over there, right? If I raise the temperature, what's going to happen? I'm going to take some population from that ground state of the reactants, the one that is currently the most populated. Population is going to shift up. As it shifts up, most of the states it's going to move into belong to the products, right? And so that suggests that I would be getting more product as the temperature went up, okay? We can think about this in terms of a very extreme example. And so this one is kind of obviously a conjured up case, but this is a reaction that's substantially endothermic, right? My energy gap from the ground state for the reactants up to the ground state of the products looks pretty large. In this case, we've declared, because I'm making these systems up, that the reactants have just one available energy state. There's only a ground state. There's no other reactant state, right? The products have many states that are closely spaced. There's some epsilon drawn on there, which just says that's the distance between those states, right? And every level there is offset by the same amount, okay? So if I wanted to go in a low temperature limit, think about the way we do populations. Low temperature limit, as the temperature approaches 0, what happens? All the population goes to the bottom, right? So in low T, in the low temperature limit, I get essentially all reactant. And if I have all reactants, that means K is tiny. Right? Because if I have my equilibrium constant is the amount of products over the amount of reactants. If I have no products, then my equilibrium constant approaches 0. Okay. So once I go in the high temperature limit, what's going to happen then? If we really go in the literal high temperature limit, let the temperature go to infinity, what happens to the populations? The populations of every state become equal as T goes towards infinity, right? So that means we have lots of reactant, lots of product rather, and that means K is large. Right, and so that it should make sense that that's what would happen, and it should make sense in terms of the picture if we think about things that way. All right, so I do want you to be able to think about some of these ideas a little bit and to use these diagrams, try and make sense of them so that you can get a little bit of intuition for why this method works. The last slide we're going to look at today in this video is this one, which actually has the result of how we would calculate our equilibrium constant, okay? So we need to then look at how to get the population distribution across all those things. And if we do a bunch of work on that, you can read some of the details in the textbook. The general result is that we can find the equilibrium constant from the equation that's on the bottom of the screen. In this equation, that pi out in front, that's a product, right? So like a sigma is a sum, the pi there is a product. What does that say? This is the mu sub I in there, which shows up as an exponent up here, right? That's the stoichiometric coefficient for each thing. Those stoichiometric coefficients are positive for products and they're negative for reactants, right? And so what does this thing do? It takes the partition functions, the Q terms, and basically it sets them up in the products over reactants framework, right? If you think about how you calculate an equilibrium constant in terms of concentrations, right? It's the product concentrations over the reactant concentrations with everything raised to a power that matches its coefficient in the equation, right? That's what this product thing is going to do. It's going to say, take the partition functions for the products on the top raised to powers that match the coefficients over the partition functions for the reactants on the bottom raised to powers that match their coefficients in the equation. Okay, and then the last piece it's got is it's got this exponential term over here that involves my delta U 0m, which we defined earlier on in this video, right? That's the thing that's going to make sure that all my partition functions are now set to be relative to the same choice of 0 energy. Okay, the version on the bottom simply takes the form we have had for the translational partition function and pops that in there, and then it leaves just rotational, vibrational, and electronic pieces like that. Okay. In the next video, what's going to happen is I'm going to take that bottom equation and do a lot of arithmetic to calculate an equilibrium constant for a very simple chemical reaction. That calculation will, again, illustrate that it's possible to do the calculation. It'll also get you convinced that it's a fairly tedious thing to do. And so I guess you have that to look forward to in the next video. Thanks.